All right, we are live now. Perfect. Perfect. Wonderful. So, first of all, welcome everyone to this webinar. And it's an online session to discuss the, also just give me a moment, I'll open the chat and Q&A window. All right, I'll just keep all the windows here. Okay. All right. Wonderful. Wonderful. Wonderful to have everyone in this discussion. This discussion is about revolution or a revolutionary idea in which the machines can generate images from text. So it is equivalent of creating an artist whereby you give a text prompt and it creates images. So we will go into that a bit more into details as we go into the session. So the agenda is that we'll talk briefly about CloudxLab speakers, and then we'll start with the Stable Diffusion briefly. And then we will cover the background topics such as neural networks, recurrent neural networks, and encoder-decoder models, and then transformers. And then we'll talk about stable diffusion components, and then the actual diffusion model and the procedure and limitations. All right. The session is going to be fairly technical. So though we will try our best to explain everything in simple most words, and we will also cover the backgrounds on the neural network, but that'll be super brief. And the session is going to be approximately of 2 hours with probably a 10 minutes break. Usually we skip breaks. And yeah, except for the speaker, everybody is on mute. You can use the chat to ask questions. In case you are joining in the Zoom, you can ask ask questions using Q&A window. All right. The recordings and the slides will be shared with everybody after the session, but feel free to take the screenshot or write about it in your own blog. Okay. All right. So all right. I don't know, what does it mean? Hey, if you don't want to be here, you can use this app to send a bot to the meeting with your name. It will record everything. All right. I think kindly avoid promotions here. I'll have to ban otherwise. Okay. So kindly avoid promotions. This is a very invite only kind of session. So, and most of the people here have come to learn about technology. So please avoid your promotions. All right. Else I'll have to ban you. Okay. All right. So kindly avoid the promotions in the chat as much as possible. Okay. Perfect. Perfect. Great to have so many audience today. And I never expected that for this technology session, we will get so many audience and attendees right now. Okay, great. All right, not only on Zoom, but also on our YouTube channel. There are lots of people. So at CloudxLab, the core vision is to upskill engineers and professionals in deep tech and deep learning, machine learning, big data, or data engineering, and make them employable and future ready. So essentially, the core agenda is that once you learn technology, the chance of building careers and improving lives is very much. And CloudxLab is basically a playground for hands-on engineering. Okay. So the system evaluates the code automatically and nudges the users by giving appropriate feedback. So what you see here is this side is the problem statement. On the right-hand side, this is a screenshot of our elements. You can try, you can sign up there for free and then start using it. On the right-hand side, you see the lab. And when you submit an answer, it checks it and gives you go ahead. All right. Not only that, our learning system provides you with complete hands-on environment whereby you can build your own project, you can do your own work, and it is up to you what you want to do there. All the tools of machine learning, deep learning, data science, AI, big data are available on that lab. Okay. The CloudxLab is an online cloud-based environment. It's a real-world experience, seamless experience. There is a centralized data set, so you don't have to rummage around for your own data sets. And you can access it from all kinds of devices. And basically, I mean, we have a social presence. It helps you build your social presence. There is a forum, there's a profile, and you can also interact with other users via messaging. We have a portal where we display our hiring partners. We also have lots of courses, so you can enroll for these courses. And specifically, we have courses in partnership with IIT Roorkee and in partnership with Intel and other similar institutions. Along with that, we have our own courses. And what we have done is we have provided something called CloudxLab Premium subscription. In that premium subscription, you not only get the lab, the access to the entire lab, but you also get the access to all the courses. So that's completely worth your money. You can check the subscription is fairly low cost. So I can guarantee that it'll be the best investment you'll make in your career. So you have all kinds of courses at CloudxLab which are available. You can sign up and start using. All right. Now, the one big question, if you have seen, right, if you have been following the news around, if you just see, right, like, have you seen Imagine or have you seen this? Okay. So you give a text prompt, it can create a beautiful image. Okay. So random things that you have not imagined, it has not seen it before. You can see that? Yeah. So there are so many kind of chat prompts that are possible. Text prompt, not chat prompts. Okay. So you can just think of something and then write it, and you'll be amazed at this. So the magic behind all of this is basically some form of stable diffusion. Okay. Now, since stable diffusion is open source and public, you can take a look at, since stable diffusion is open source and public, we want to deep dive into stable diffusion rather than other papers. Okay. Now, so what exactly is a stable diffusion, right? So the first thing is a text-to-image diffusion model capable of generating photorealistic images. Okay. And about myself, somebody was asking, I think you already saw it here. So I started my career with just after my college from IIT Roorkee, I went to DE Shaw, Then I started a company called Dbits. And then I worked with InMobi, Amazon, and then I started I started something called No Big Data, and then we got an idea of a lab, so we changed the domain name and moved everything to a new company called CloudxLab. And the CloudxLab is something that has been running and it is going well. And as of today, we have more than 200,000 learners on our platform. And I mean, I think what we have done great is providing and stitching all the content with an online lab. Lab means not lab means a full Unix environment equipped with all kinds of tools that are really useful open source tools. So that is the whole vision, and it has changed lives of people. I have like lots of people who have gone through my courses. They are architects and principal engineers at various places, even CTOs at various places. So I'm very proud of what we have done at CloudxLab and No Big Data. Now, so that's about me. I hope that's clear to all. All right, let's, without further delay, let's just jump into it. So stable diffusion is basically a open source model which converts a text prompt to image. And it's capable of generating very realistic image. Okay. Now, sounds like a magic. It sounds impossible. Okay. Like, look at this prompt. A beautiful, cute, fluffy baby animal with a fantasy background inspired by Leonardo da Vinci. And in 8K resolution, you can see that it is it has generated such a beautiful image. Now, there are many such animals possible, and you can try again, and you can see that every time you will get a new image. So you can, right? I think you can just see if you go to Stable Diffusion online, you can, even here, you can, right? Yeah, there's an image and video and all of that. Like, and they are crazy. You can see, these are all generated by similar models. Okay, so if you see Stable Diffusion, right? So this is the website, the website which basically has done that. Okay, like for example, tiger made food grains being eaten by let's say deers. Okay, I've not generated it before. I'm just trying it now. Okay, those who are interested, they can go to Stable Diffusion Web and try that out. Okay, I hope it'll finish. I think it'll take some more time. Feel free to ask any question if you have. It has tried, but yeah, just tried to create something. All right. All right. It has tried to meet. All right. One of the questions that usually come up is that in business context, where are we going to use stable diffusion, right? The thing is that it is fairly new revolution that has started. So a lot of new innovations are happening in this. Okay. Like, for example, um, I was talking to somebody like who is like new age designer. So what he does is that he comes up with these nice detailed prompt for, he was using DALI, DALLE. That's a similar model from OpenAI. And what he was doing is that he was basically creating new designs of new patterns of the clothes. And that is something interesting. That's very interesting because there are new professions that are coming up. Okay. Where people are utilizing this power of AI in order to innovate creatively. Not only that, the similar technology is also used in, let's say you are given an image and you have to do an image editing. Similarly, this can also be used in creating posters for the business promotion. See, what do people from marketing do? They create the visuals to go on an ad, to go on a pamphlet, to be printed, and so on. Most of that work, like really creative work, can be outsourced to AI. All right. And okay, I hope the YouTube live streaming is going well. Let me check. Yeah, it seems to be going well. Okay. Okay. So another question that usually comes up at this point is there a difference between DALI and stable diffusion? So yeah, so DALI was not open sourced. It was their internal. They did publish their paper, but the details were not, I mean, available in the wild. Specifically, the database and other things were not available. Okay, so that's the core idea. That's the core difference between the two, and also in the approach, the way the neural network is trained, that was also different. Okay, but the core idea is that take the text, convert it to some meaningful numbers, and using a model which has been trained on really large database, and then once you have these numbers representing the text, which is these numbers represent the meaning of the text, using these numbers, creating an image. Okay, that's the simple idea. In very simple words, I would say text to bunch of numbers, and from bunch of numbers, creating image. That's the core idea. And this process has been done slightly differently by Imagen, by Google, OpenAI, DALI, and Stable Diffusion by another set of researchers from our university. All right. It can also be used to edit the images. Okay. You can just say, this is the initial start of the image, and then you say, replace the dog with a cat. So you get the cat. Okay. So image editing, marketing materials, and so on. And you can start using just the DALI or other tools available, or you can just use Stable Diffusion itself for your own work if you don't want to implement from scratch. But understanding the underlying philosophy is extremely important. Now, many people ask at this point of time that why should I learn it? What is the point of learning this when I can just use these models? There are a couple of reasons for this, right? We need to reinvent the wheel, not because we need too many wheels, but we need inventors. Therefore, um, it is important to understand the architecture of the wheel and try to reinvent and so on. And that essentially opens your door to new career, new inventions, and so on. I mean, that's the main philosophy behind me giving architecture level details of stable diffusion. Similarly, we also did deep dive into the architecture of ChatGPT so that you can learn about what it is and how it works and probably reinvent in that game. So it's not about reinventing the wheel, it's about creating inventors. All right. Therefore, do not hesitate in learning new architectures. The other reasoning is, in which you'll find it useful, is that if you go for AI researcher or AI scientist or those kind of roles tomorrow, you will be asked these kind of questions, a complex question, given a big set of videos and audios. Can you make it smaller? Like, can you, from 100 hours of videos, can you create, say, 2 minutes of interesting video? Okay. So unless you have seen these architectures, unless you have gone through these architectures, you won't be able to answer those questions. Okay, if you have gone through these architectures like ChatGPT architecture or this one, you'll be able to imagine and create. I mean, we will be able to clear those interview process. Okay, so that's a very important point. The way machine learning interviews have evolved over last, say, 5-6 years is just remarkable. Earlier, people were asking very simplistic question about regression, decision trees, this, that. Now the questions are very different. Now the questions are more like, how would you, given the text, how would you create a video about it? Okay. So those kind of things. So unless you go through these architectures, you won't be able to answer, you won't be able to handle the machine learning system design interviews. Okay. All right. The other advantage of the stable diffusion kind of models is that we take the low resolution image, improve its quality. Okay. Now, I will break it down into parts, into smaller parts. Okay. And right, because stable diffusion is essentially on a composition of many complex ideas. So I want to start from really, really simple things, really simple things. Okay. All right. Before moving ahead, there is one interesting question. The question is API available for stable diffusion model? Stable diffusion is available in open source, so you can download it and use it. Okay. And you'll be amazed to know that so many open source models are available and you can play around with that. All right. Now, question is, where can we usually implement stable diffusion in business context? Yeah, I think that I've answered already. Okay. So if you're asking a question, please use the question window, because I'm going to keep my eyes on the question Q&A window or the YouTube chat. All right. Perfect. So the first question that comes is, how does a machine learn? We show it data, history data. How does it learn? How it figures out the meaning of things. Okay. All right. Now, okay, so yeah, the AWS or Google would be providing something similar on their cloud, or you can just spin off the machine there and do it. Okay. I am not an expert at AWS and GCP, though we use it, but you can just check their website. The important part to understand is that my request to everybody, it might look impractical, right? Because everybody's common sense as of now is, just take AWS or GCP and, you don't need to learn anything. You don't need to do anything. And my request is that even if you use any pre-built model, even if you use any pre-built API from OpenAI or like anybody, still you need to know what's going underneath. Okay, it's for your welfare. Okay, when you go for an interview somewhere for hiring, nobody's going to ask you that, do you know how to use AWS or GCP API, right? It's pretty straightforward and it's not even a skill. Okay, people know that. The important part is that when they will be asking, a really good company would be asking you these kind of hard questions, like how would you achieve this? How do you achieve that? And that will help you a lot. Okay, cool. Thank you for that question. Moving ahead. Now, question is, how does a machine learn? And that's a very important question. Okay, because it seems that if you have like historical data with the labels, machine can learn anything, but how does it learn? Okay, right? So we are going to, there are many ways of learning, like the way machine learns. There are many ways, like plotting a graph, fitting a curve, fitting a plane, and doing SVM, creating a decision tree automatically, and so on. There are so many tools out there. There are so many machine learning models out there that basically do that. But we will focus more on neural networks. Okay. So the neural networks is essentially inspired by the structure of the brain. And the way you can visualize is that we feed the input and we have an expected output. And this is like a neural network. The way you can think of it, the connections between neuron is these knobs. You see these knobs? These are connections between the neurons, Okay, we call them synaptic nerve in the human brain. In case of the artificial neural network, we call them weights, the connections. Okay, so what you see is that these connections are basically a bunch of knobs. We twist them around and we twist them around such that the output of this neural network matches with the actual output. We put an input image or input text, expect something output, and then we keep on twisting these knobs until that is matched. Okay, that technique for twisting these knobs until it fits the input, until it fits the output with the expected output, that process is called backpropagation. And you can take a look at our backpropagation from scratch tutorial at CloudxLab. So the idea is pretty simple. You feed the input. Input could be an image. Input could be a text. Input could be random numbers, right? So usually everything here is going to be a number. Now, question you might ask that, hey, how do you convert the text to number? I'll talk about that. So here we feed the input, we have some expected output, and then we twist these knobs, and that's what we do. Okay, so we basically, given the past data, we keep on twisting these knobs so that the output is matched. Okay, now once we have trained the model, what do we say that, okay, we have trained the model, right? When we are done with twisting these knobs, okay, we note down the positions of the knobs, And those positions is what we call the trained model or pre-trained model, right? And we basically take that to production or a server machine where we are going to do inference. There we don't do the training. And these knobs basically take the unseen input and provide the output. Okay. So essentially, this is the inference phase. This is the training phase. In training phase, we figure out the positions of these knobs. And inference phase, we figure out we do not twist these knobs, or we do not train the neural network. We basically take the unseen input and it just uses these knobs and gives the output. Okay. The way you visualize is that these are neurons, and those knobs I was talking about are these lines connecting these ones. Okay, these lines is what we are twisting all the time. So this is the neuron, this is the input, and there is another set of neuron, and everything is connected. First layer, every element is connected to the second one. Okay, so if this has, let's say, right, approximately it's a total multiple of this multiplied by this multiplied by this, like 5 multiplied by 3 plus some more numbers. That's the total number of weights that we need to figure out, the total number of knobs, total number of connections, right? So and this is the output layer. Okay, we feed the input, we get the output. Okay, using the back propagation, we keep on tweaking this in the training phase. Okay, now this is like a really high level overview. If you want to learn everything from scratch and want to try it, go through CloudxLab courses or go through our blog on backpropagation from scratch. All right. Now, question is, how does this model outputs a word? Okay. So question is that these models were taking numbers as input and giving numbers as output. How does it handle text? Okay, so the way it happens with the neural network, we convert these inputs into numbers. And how do we convert those into numbers? We give each word some sort of ID, like 1, 2, 3, 4, 5, and then we convert that into basically it becomes like a big matrix. Okay, so the is represented by, say, 10,000 numbers. Imagine that you have a dictionary of 10,000 numbers. So the is represented by 10,000 numbers. All of them except for the is 0. So it's like 0, 0, 0, 1, 0, 0, 0, like that. Okay. Similarly, cat. So out of that 10,000 words, only that cat is 1 and rest are 0. So that's how we convert one word into a vector, into a bunch of numbers. So each word is converted into that. This is not what we call embedding. This is just a way of representing a word. Okay, so we feed this input into the neural network. Like if it's a generative model, the generative model, like the chat GPT or something, we feed these a bunch of words into as an array of numbers, and feed that to those bunch of knobs called neural network. And this neural network gives you these output, which is number, and each output has a probability. Okay. Each output has a probability that, okay, first one has got this probability, fourth one has got this, and therefore fourth is play. Okay, like that. And so essentially, this neural network is taking this as input. Most of these text generative model, you must have heard about GPT and chat GPT. The way they are trained is that they downloaded all the text from the internet. They made it autocomplete a sentence. Like, for example, here we are saying that the cat and the dog play, right? And there could be many other suggestions at this point of time, right? Therefore, there could be like 100 suggestions here, and there will be a bunch of probabilities of each of them. And we pick usually the highest probability, okay? So essentially, this is a way of auto completion of, this is a way of training neural network. Now, what happens is that when you keep on feeding this data over and over about all of the internet's data, this neural network starts understanding the meaning of words and sentences and the context and so on. Okay, that's how most of the text models are kind of pre-trained. Okay. All right. I hope this is clear to all. This is essentially a very simplistic way of giving you a kind of intuition that what's going on. How do we represent the text as numbers? Okay. Now, how does it take a sentence as input? Okay. How does it take a sentence as input? Okay. Now, you must have seen that, okay, we can do the predictions based on a word, but how does a model takes the full sentence such that it can, correlate the meaning of everything? So to do that, people invented something called recurrent neural network, okay, which basically many of these words, and it basically we feed it as a chain and it learns from all of that. Okay, so long back, recurrent neural network were something like this. Okay, it's the same neuron. We are first feeding the first word, then second word, the third word, and then fourth word, and it's giving out the output. Okay, so essentially, this is how we always fed sequence of data. Okay. Now, afterwards, people came up with really, really cool ideas about things. One of the greatest idea that will be quite useful in discussion of stable diffusion is called encoder-decoder pattern. Okay, what does it mean? Imagine that you have lots of images without any label. Okay, you have millions of images without any label. Can you train your model to, create the new images automatically? You remember that thing called this person does not exist. Okay, you must have seen that. All right. So the way those kind of models are trained is using encoder-decoder pattern, right? You must have seen this person does not exist. Okay. So this is a created image. Okay. This is a created image by something called generative adversarial network. Okay. And you'll find that people have figured out how to do these kind of things. One of the greatest idea that came in the history was something called encoder-decoder. Okay. Meaning we feed a person's image, a human's image, face, and we expect it to generate the same image back. Okay. And here, what we do is we basically, what we do is we make the neural network such that, okay, that the face is represented by 100 numbers. These are 100 numbers. So this neural network is translating the face. This is, let's say, somebody's face. Okay. And this neural network learns to convert this person's face into, say, 100 numbers. And this neural network is converting these 100 numbers back to face. Okay. Now, so what you do is you cut this part. Once you have trained this neural network, what you do is you cut this part and you start feeding random numbers to it. Okay. And you'll find that it will start creating new faces. It will start creating new faces. And that's one of the greatest techniques in past. Okay. Further, lots of people, what they do is they basically they take a very good image. Okay. They take a very good image. These are very important ideas, I think. So imagine that you have a very nice image. Okay. Very beautiful image here. Okay. And what you do is you take this image and add lots of noise around it. Okay. Just add lots of noise. Okay. Almost make it like indistinguishable. And then you train this model saying, here is an ugly image, here is a dirty image, and this is an expected output. Can you learn? Okay. Can you learn? And amazingly, these techniques of making the image noisy artificially has worked really, really well. And that's another pillar of stable diffusion. Okay. I hope this is clear to all. So we artificially have created this data without any, labels. Nobody's telling like what is coding and what is this, what is that. You have, let's say, a million image, and we are feeding the same image, expecting it to create the same image output. And just that we have throttled it, right? First bring down the whole image into, say, 50 numbers. And then second one, we give those 50 numbers and say, can you create this person? All right. So all right. Moving on. Now, there's a question which says, if words is not available, what tokens will be generated? Okay. I do not quite understand that, because if you do not have any input, you can't generate the tokens. Okay. The tokens are essentially giving them number, like this is first word, this is second word, third word, fourth word, like that. Okay. So the purpose of generating tokens is basically to convert the text into some numbers. All right. Now, the other advancement of encoder-decoder pattern was with respect to the language. Okay, so same encoder-decoder pattern, this one. Inside each of the encoder, we are feeding a sentence. The sentence is what we are feeding. Like in the first step, we are feeding milk. Then the second one, same neuron, we are feeding drink, then I. And this one, after we have finished it, okay, it's passing bunch of numbers here. It's passing these bunch of numbers here. Okay, so this is like the meaning of the sentence has been put forth into some bunch of numbers here. Okay, now what you see is this decoder pattern, very interesting part. Okay, what we are trying to do here is doing the machine translation, converting English into French. Okay, so we fed a sentence, it gave us a meaning of this. Okay, the encoder translated this into bunch of numbers. Okay, now here we are feeding French in the same way, doing exactly same thing what we did here, giving ID to each words and so on. Okay, and then we're feeding these bunch of words here. Now you got the meaning of the sentence to be translated, and you got, let's say, the word go, right? A symbol. So here it produces next word to speak. Then we feed we feed this word back here, and then it tells us the next word. Then we feed this word back here, and it tells us the next word. This is exactly what GPT or ChatGPT does. Okay, it produces one word at a time. It produces one word at a time, and then we feed it back, and so on. Okay, so this is essentially the machine translation encoder decoder model. Okay, right now I've demonstrated it using something called LSTM. Okay, or you can say recurrent neural network. This is a neural network in which, say, to same neuron, you keep on feeding the values and keep on extracting the values at every stage. Okay, so yeah, I know that there are too many ideas, but just very simple thing is you can think of this as a black box. It takes a sentence, gives you the meaning of the sentence in a vector, right? When we say meaning, meaning is just bunch of numbers, okay? And we do not hard code it. We let the neural network figure out what those, intrinsic meaning of the sentence is, or coding or embedding is, all right? And then this what is going on. So this is the encoder, decoder, or transformer, or machine translation model. That was, again, another breakthrough in the history, which is used at lots of places. Now, people came up with something so cool. It's called a transformer model. It was, again, another breakthrough. Over RNN, recurrent neural network, people went into this amazing idea called transformer. Specifically, one big trouble that people had in neural network was, how do you handle time series data? How do you handle the sequence of data, right? So for that, people realized that one of the groundbreaking idea by, I mean, in this paper, if you take a look at this paper, just amazing paper, okay? And all right, this amazing paper called Attention is All You Need. Okay, attention is all you need. Just a second. Yeah. So this paper was one big groundbreaking research for almost entire research in AI today. Okay, so based on this paper, Ashish Vaswani and other team from Google Research and University of Toronto, they basically did this groundbreaking work, and that led to transformer. Okay, so there was no need to use RNN. A question from Dinesh is GAN model and transformers backend technologies are the same? No. So the generative adversarial network uses transformers and other things in order to create images. Okay. The transformer is essentially a very fundamental building block of the neural network. Okay. And so essentially what it does is it's essentially another neural network. Okay. The only difference is that it can take a context and a sequence of input, and it can give the summary. Okay. And in case of transformer, the transformers use lots of building blocks called attention. Attention essentially does one thing really good, that given a context and given the current input, it basically applies this context and gives you the output. Okay. And I mean, rather than looking at lots of maths underneath, you can see it like it can speak in the context. Okay. Usually what happens in the neural network is this gets translated into this. But in case of attention neural network, This gets translated into this after applying the context. Okay, so wherever you have a context, you have a sequence of input to be fed. There, you use the attention model. Sometimes you don't have a context, so what you do is the output of the summary of the previous step, you feed it back, and that's called self-attention models. Okay, so essentially, if you have to translate something from one language to another, the translation model, the machine translation model turned into this. So you are feeding, I am a student, and that's producing the meaning of it. We call that context vector. And then it starts producing based on the context and the next word is spoken, it starts producing the outcome. Okay, so first we are saying end of the sentence, so it produces J, and then we're feeding J back, and it is producing the next one, the next word. Then we are feeding it again back here. Then it produces the third word, and that sequence keeps on going. So keep in mind that when we are in case of even GPT or any of these model, what we usually do is first we just append this end of sentence token at the end of the input, and then it gives the next word. We start feeding it again and again. So to generate 1,000-word response, okay, 1,000-word response, how many times the model is called? How many times we'll be running this model? 1,000 times, right? For one word, the model is being called once. Okay. That's why you must have seen that ChatGPT keeps on giving you one word at a time. All right. So this is basically attention mechanism. There are two other concepts called multi-head attention and position. You can take a look if you're interested, because this is when you compose that basic building block of context and the input, and you get the output. You combine lots of those things together to build a transformer. We call that multi-head attention. Okay. And then there's something called position embedding. I would suggest that take a look at the position embedding as well. The idea is very simple, that along with the word, we also feed the position of it. Okay. And this is the transformer architecture, the classic transformer architecture, but you don't need to understand each and everything in this. So we will basically just give you a simple idea that here, when we are anywhere, we are asking the system to generate inputs or generate images or generate text or images, you basically can use transformer. Okay. Now, moving ahead. All right, how do I clear it? And moving ahead. So most of these models use something called transformer decoder. Okay, we basically don't have an encoder. We essentially use this. All right. Now, after this, I mean, I did not want to go too detailed into the transformer. The most important thing I wanted to tell you was the encoder decoder pattern. And the other thing I want to tell you was the self-attention and how do the neural network trained. Okay, so with that, I have my colleague Shubh, who basically is a machine learning researcher with us at CloudxLab, and he is working with us into machine learning engineering and the research. So he will be presenting the stable diffusion architecture, and I'll be around, and feel free to ask questions. All right, over to you, Subh.
Yeah, so thanks, Sandeep.
It'll be great if you can share the screen yourself.
Yeah, I can. So yeah, so I've shared the screen. Is my screen visible?
Yes.
So yeah, so hello everyone and hello Sandeep, and thanks a lot to make my work easier by explaining the concept beforehand. So yeah, so let's see how the stable diffusion architecture works. So what is stable diffusion? So it is as Sandeep told, it is a generative model. So it is used to generate images, and the input can be text or an image. But yeah, it's not first of its kind. The first was generative adversarial network, which was introduced in 2014. So yeah, it was a game changer in the domain of machine learning, because people thought machine learning can also be used to generate data and all. So it was literally a breakthrough in machine learning domain. So yeah, so how GANs were able to generate data? So it was they were composed of two components. One was generator and one was discriminator. So yeah, generator was used to generate data and discriminator was used to tell if the data is fake or not. And then on the basis of the output or review of the discriminator, the generator was updated. So
Right.
so this was the ongoing training process of the generative adversarial network. So and when the generator was trained and it was completely trained, then it was able to generate the data which was it seemed much real, and it was not fake. So yeah, we used the generator part to generate the data. So yeah, but there were several problems in gens, it used too much of training data, and also training it takes too much time, even up to days to months.
Yeah.
Also it was not able to generate diversified images. So yeah, so to
The
address.
the other problem with the GANs, I think, was they were unstable.
Yeah.
Okay. So it's because there are like two brains competing with each other. One was generating, another was discriminating. If both of them start agreeing on things and do not improve upon, right, it becomes like if on the road everybody is walking on the left hand side, we call that mode collapse, and that was a big issue with GANs and other things. Okay, wonderful. Yeah, go ahead.
So yeah, so this was yeah, Sandeep, you told right. So that was the limitation. So then come diffusion model. So it was first introduced in 2015. Yeah, it is famous. It has become famous nowadays, but it is from 2015. So yeah, let's see how it works. So yeah, so this is the architecture of the stable diffusion. So the stable diffusion is introduced in I guess previous year 2020 or 2021. So this is the whole architecture, like how it works. So yeah, it takes the text as an input, and then there is a text encoder which encodes the text, Sandeep told it, the words and words are to be represented in tokens to be understood by the machine. So yeah, so the text encoder does that part. Then there is RNG. So RNG is nothing it's like a random noise generator. So it generates a random noise in the form of image, and we will discuss more about it in later, like why is it necessary. Then there is a diffusion model. So we pass the encoded text and random noise to the diffusion model. So it then generates some information which is decoded by the decoder, and there here the image is outputted. So yeah, this is the general workflow of the stable diffusion. So let's dive deep down into every component of the diffusion model. So yeah, so first we will discuss about the text encoder part. So yeah, what is really happening here? So yeah, so the text encoder part of stable diffusion uses clip model. Clip is an OpenAI model, which is a transformer based model. To be more precise, it is based on the GPT architecture, like the same architecture which on which ChatGPT is working. So it uses that clip model from OpenAI. So what does it does is it takes the text as an input and outputs text embeddings. So the embeddings, how the words are represented in the machine language. So those are embeddings, like Sandeep showed. So yeah, that's it. So yeah, this is how the clip encoder was trained. So it is generally it is the training process of the clip encoder. So it is a combination of two models. The one is text encoder and one is image encoder. So we pass the text to text encoder and image to image encoder to generate the encodings. Then we compare them with the cosine similarity of them. Cosine similarity is the way to compare how similar two embeddings are. Not only it is not only limited to embeddings, but yeah, here we have used to compare how similar two embeddings are. So yeah, so we encode both text and image and then compare their embeddings using cosine similarity. Now we update both the models using the result. if text like when the model would have started the training, then the text and image would like vary very much, to be honest. Then but slowly after the training, as the training goes on, so text we can see like the text encoder can generate such text which is too close to image, like if we like here we have output of the pepper, the ossipov, that means I guess the dog in a grass. So like the image also resemble that. So after training, the clip encoder is able to generate the text is the encoding so good that they resemble the image, because it learns how to capture the information by updating the model. And how the model is updated, it is by the back propagation, which you can see in our
A quick question, Shub.
yeah.
In case of the clip encoder, this text is being converted into this bunch of numbers, T1, T2, T3, Tn, right?
Mm-hmm.
So is this encoder pre-trained or it is freshly trained in this
It is
process?
currently during the training process. Like I am explaining the clip encoder training part. It is different from stable diffusion. So like it's important to know how it works. So
Okay, okay.
it is a training part. Like first it is an untrained text encoder and untrained image encoder. So like we give the input, text input and an image input, and then it generates like this embedding for text and this embedding for image. Then we compare the both the cosine, both the embedding by cosine similarity, like how similar they are. Then we update both the model using back propagation, the text encoder part and image encoder part. So at the end, the model can generate text so accurate according to the image. So that's the whole part of the clip encoder.
But in the end of this process, we will only utilize text encoder only, right? The image
Yeah,
encoder one.
I'm coming into that. So yeah, a trained model will be able to produce embeddings where an image of a dog and the sentence, a picture of a dog are similar. So like it captures the image to see natural images are not just random. They capture like spatial relationship like for an example, an image of a dog will be like an image of a dog, image of face with a four-leg animal, or like face image of a face. So it also represents several spatial relationships like nose or ears, and they're connected like so. Natural image are just not random. So like this is the like that. So this is how the trained model produces embeddings where like image of sentence and images are similar. So yeah, so this is the encoder part, and we only use the text encoder part of the stable clip encoder, so to generate the visual representation. So it's like text encoder so the embedding which will be generated of this text, like an astronaut riding a horse, it will be too similar to its image, so it will be too meaningful for the stable diffusion part. So this is how we encode the text to the stable diffusion. Now what is diffusion model? So yeah, it was so I told you, so it was you to like it was a breakthrough after the GANs. So let's see what is the diffusion model. So yeah, so as a diffusion model is a generative model, is much like GANs. So it works in two parts. One is forward diffusion and one is reverse diffusion. So here, as we can see, the image, the input image which we provided data, it is like we add noise to it in steps, like in every step some noise is added to it. And then see the main idea, let me tell you about the main idea of diffusion model. Suppose like and diffusion term was coined from the idea, like the concept of diffusion and science. So yeah, so like suppose there is a piece of paper and a drop of ink drops on it. So after some time the ink will like spread on the whole piece of paper. So now we can't tell like what was the origin of the drop of ink, like where it really originated. But what if we can tell the origin, like so what here the ink, the spread ink is like a noise to the piece of paper. It's like this rubbish noise, so it is noise to the paper. But if we can predict what is the origin of the noise, then we can use it to like subtract the noise, and then it will give us the output image. So this is the concept used in the diffusion model. So what we do is like we train the noise predictor. So like what is the use of the noise predictor? It predicts the noise in the image, and then we can just reduce that noise for the image, which will give us a more clear representation of image. So this is the like more general understanding. So let me describe it more detail. So like it works in two parts. One is forward diffusion and one is reverse diffusion. So yeah, forward diffusion, how it is done is like first the input image is corrupted by gradually introducing noise until the image becomes complete random noise. So like as I told, like if we introduce noise in the image, so unless up to it becomes random noise, and we add different amounts of noise to a single image. Like this is a cat image, so it will like generate four more images. Like we add a noise one amount of noise to generate image one.
But quick question, Shiv, that how would we ever know that it has become a complete noise?
Complete noise. It is like so I will come into it like okay, give me let me give you a like general overview. So like there is scheduler component in the diffusion model, which is whose task is to like predict like how much noise to add to the image. So it is responsible like it is also a neural network.
Okay.
It decides like how much noise to add to the image to make it like is it a complete noise or like it is a little noise, like so the scheduler component is used to predict it.
Cool. Yeah.
So we add different amount of noise to an image. And what is the output? So like we can like from a single image we can generate like tens of training example per image, like or even more if we want. It totally depends on the amount of noise we are adding. So this is the benefit. Like as I told, like giants were suffering from like the less of data set, because we need lots of data set to train such huge model. So this is how we like solve the data set issue by generating like more of the dataset by single instance. We can generate like tens or even more, but just by adding image. Then like so yeah, as I told, the main task of the forward diffusion is to train noise predictor. So like how we do that? So we pick a training example from dataset prepared in the previous step. Like in the previous step we prepared a dataset, so there will be lots of dataset. This is a single image and we have produced like 4 images of it. So like we will have lots of dataset. So yeah, so we can pick a training example from it, and then we use a unit model to predict the noise. So like a unit model, and also there is a scheduler component. So like a unit model is just a neural network which is used to predict the noise. So then we compare it to the actual noise. Like we also have the input noise, that's what we outputted, and then we calculate the loss, and then we update the model using back propagation. So this is how the noise predictor is trained. So after training, the trained noise predictor can take a noisy image, and the number of the denoising step is like this process is completed in steps. Like one step will use to predict the noise, and then another step, like we can decide any. These steps are generally called sampling steps. So yeah, this is how the like training the noise predictor is trained. So the final model will be able to predict the noise in the image, and this was the whole idea behind diffusion. So yeah. So then comes the most important part. So this is the most important part of the diffusion model, which is called reverse diffusion. So yeah, so how it is it is work is like it generates a completely random image, like completely random. So, you can see here, it is just noise, like what I was talking about, that RNG, random noise generator. So we have a component like that here, and it generates a complete random noise. And then we ask the noise predictor to tell us the noise. So like if like the unit plus scheduler model, we use that to predict the noise, and we use the pre-trained. Like for now, the unit model is trained completely to predict the noise. Then we subtract, like suppose this is the predicted noise here, and then we subtract this estimated noise from the original image. So like this is the original image, which was a complete random image, complete noise. Then we predicted the noise, and this is the unpredicted noise. And then when we subtract the predicted noise from the image, this is the image, the step one. This is the image which is calculated, and this is the step one. So as I told, so like river diffusion is completed in several steps, which are known as sampling step. So yeah, so this is the image which is outputted after the first step. Again, we will repeat the process. Again, the unit will tell like how to to predict the noise, and this time it predict this noise, then we again subtract it, and as we can see in step 2, it we get a more clearer image. And this is we keep on repeating up to like the predefined sampling step, and then the output will be like fourth image, which is here. So as we can see, it is more clear, and we see the input image, so it was completely noise, it was complete noise, and then this image is like more clear, and it is a representation of cat. So what we did in every step, we just used the unit plus scheduler module to predict the noise, and we just kept on subtracting the noise to output a more clearer image. So this is the idea behind diffusion model. So yeah, so goal of training a diffusion model is to run the reverse process to generate new data. And after training, the diffusion model can be used to generate images by simply passing randomly sampled noise to the Latent denoising process. So this is also called it the denoising process, because as we see, we remove the noise. So this is called the denoising process, and it is the main idea behind the reverse diffusion. So the trained diffusion model, the trained diffusion model will be able to generate images by passing randomly sampled noise, which we like. Here we passed. Here we generated 64 into 64 initial noise patch. 64 and 64 are the dimensions of the image, and we generated it, and we passed it to the diffusion model. So this is how the diffusion model will generate a meaningful image out of the noise by just subtracting the predicted noise. And how it predicts noise? It is from the unit. And how unit is trained? By backpropagation, by comparing it to, see, we will have data. Okay, one doubt can come, like how we know what is the actual noise. So like when we add the noise, we keep track of it, like what was the actual noise we add. So that is also one task of the scheduler component. So we then it's like there's a particular step. So we pass an image, and we then add a noise in a step. Then we will keep track of the noise information, and at the end we will compare the we will use unit model to predict the noise at the starting of the training. It will it will give a very bad prediction. So we will then compare the actual noise to the noise which we added, because we beforehand know that how much noise we added. So we compare the predicted noise and the actual noise, and then we calculate the loss, and then we update the unit model according to that. So yeah, this is the whole idea behind the diffusion model.
So basically what I understood is that what we have, I mean, let me rephrase whatever you said. What we are trying to do is, given the noise, how can we create a person or an object or image? Okay. So basically, there are two things that are acting here. One is the noise, and other is the meaning of a sentence given by the unit, right? Not unit, clip.
Yeah.
So clip gives the meaning of the word, meaning of the sentence, and then there is a noise, and then it gives the.
Yes, Sandeep. So until now we have not included the text part here. Okay. It is let's see, the random noise also, as I told, nothing is totally random. Random noise also means something, but the difference will be it will not generate image according to what we want. It will sometimes generate image of a cat, or sometimes image of a dog. So to control it, we use the clip encoder part of it.
Okay.
So that's how it works.
Okay.
Now, how stable diffusion model uses this diffusion model? This diffusion model which I am talking about, it was introduced in 2015. So now the stable diffusion model, which is introduced in 2020 or 2021. So how it utilizes diffusion model? So it takes random noise patch, here is the RNG, and it takes the 64 into 64 initial noise patch. So it is just random noise. And text as the input, and the text is encoded by the clip encoder, as I told, and then we pass it to the trained diffusion model. As I said, trained diffusion model. Well, this diffusion model is able to generate images from random noise. This is trained. Now, how it does? So it happens in diffusion happens in multiple steps, as I told, where each step predicts the noise in the image. So here I have here the loop is of 50. So it will be done in the 50 steps. So how? So when the random noise image will be passed, so it will first predict the noise in the image, then it will subtract the noise from the original image, and then it will add more relevant information that better resemble the input text to the noise patch. So like how it will do, I will explain it further. So yeah, this is like how, so image and subtract the predicted noise, and this is how it outputs. So this is how. So as you can see, it's like in steps one, it is complete random noise, and then it is little less random noise, and over the steps, like at the 40 steps, it is like much more meaningful image. It is the image of a castle with some trees and all. So it was generated by the diffusion model, and this image is to like demonstrate how the diffusion model generates images. So yeah, and this is the like part of the text to image task. We can also use, as I told, stable diffusion can also be used to image task. So how it will do that? So like that we all in a image to image task, we don't provide like an initial noise patch. We don't include the RNG component. Instead, we pass the image and encoded text. Like if we want encoded text, like for a task like which Sandeep showed, like a dog on the bench, we converted it into a cat into a bench. So like in that for that task, we will we will need encoded text. But if we don't pass, like that, there was also an image with a which was converted to low resolution to high resolution. So it will not be meaning like much information, like what will be the text prompt input. It will be most like generate a high resolution image. So it doesn't like mean a lot. So so yeah, so encoded text will be like optional. So yeah, so we like pass the image which we want to generate, and then we like add the noise to it. This will be same like forward diffusion like we did. So we add the noise to it, and then like why do we like we need to add the image? That is to like blur the parts which we don't need in the output image, like a dog on the bench, and we want to convert it into a cat into bench. So here the dog is not needed. So we will just input a noise instead of a dog, like so yeah. So we will just input a noise instead of dog. So like the image will be like a bench, and instead of dog there will be some random noise. Then the process will be same. We will use reverse diffusion. So then it will like act like this image, and then we will just subtract use the unit to predict the noise, and then we subtract the predicted noise and the output, and also we will have the text input, like if we need a cat on the bench, so it will just keep on adding more relevant information to be more close to the text, and then at the end we will we have an image like a cat on the bench, like which Sandeep showed. It was a much before, I guess. Yeah, this one. So yeah, so the dog, as we can see here, a bench, the dog is disappeared. So this is the random noise which we are talking about. Then and then it adds.
So the question is that in such kind of editing, instead of random noise, will we feed the first dog image?
Sorry.
Instead of a random noise,
Yeah.
will we feed the image of a dog? Is it?
Yeah. So that that was that's what I told. We will not include the RNG part here. So
Okay.
what the RNG part does is like random noise generator. It is when we not pass an image, but when we will already include an image, then we will not include the RNG component here, and we will pass the text with the image, and this
Okay.
image will have some meaning. But
Okay.
we will pass it to the forward diffusion, and then it will like add noise and like a dog on the bench, as I explained, a dog on the bench, the dog part is not necessary, as the output is a cat on the bench. So it will reduce the dog part by adding some noise instead of it. So
Okay.
that's it. Like it can also use like in the example a tag on the bench. Like here, let me explain. As you can see, it like it the
So,
random.
so it also means that we can progressively improve an image, right?
Yeah, that means the same. We can progressively do that. So like here, like when the dog was removed by the like stable diffusion, so we can say that it produces a like much correct image of bench. Like the backward components are much clearer. So this is how like it works in the process. Like it will first remove the dog by replacing some noise, and then it will like generate the noise more like the surroundings, like how the surroundings look like, and so it will this is how is it possible to generate a good image of a bench, so that, and then it will add cat to it. So this is how it works. So yeah. Yeah. So yeah, so as we can see, it's at starting it is a random noise, and then it is after 40 steps, it's a much meaningful image of a castle, and it looks quite good, by the way. If we train it for more steps, then I guess it will be output a much more good image. Now the best part comes how text is fed into the image generation process. Like what it should mean something. So here where come the magic of the transformer, so we can say clip in transformer. So what it does is like it uses as Sandeep also explained the attention mechanism in the transformer. So yeah, it uses this. So the stable diffusion unit has a cross attention layer to provide them with the ability to condition the output based on the text description provided. So yeah, so cross attention it generally emphasizes the part of the text like we want to modify the image according to this text, so it like provides more emphasis on that, and the model is work according to that. I will explain it more like clear in in later. So yeah, so why now as I told, the major drawback of Gench was like Gench and even diffusion model, it was like they are like literally too slow to like even train, like it take days and months to train them. But stable diffusion overcomes that problem. It is much faster to train, but how is it possible? So here comes the magic of latent diffusion. So as I told you, stable diffusion is a latent diffusion model. And what is latent diffusion model? So yeah, so stable diffusion doesn't work on the pixel space. Instead, it works on the latent space. Like what is the pixel space? Is the image, what the image where the image is, it is called the pixel space. But diffusion, like in the stable diffusion, works on the compressed version of it. So like we compress the image to a little lower version, and we then work on it. So we don't have to work on a high resolution image, and that automatically make the process much faster to train, because suppose there are millions of images, and we have to train our stable diffusion model on that. And now millions of images of 1024 into 1024 resolution, they will be much harder to train, and if we can convert it into 64 into 64, and so you can imagine like a time can be saved exponentially. So this is the miracle of the stable diffusion. It uses the latent space. So the paper called this to departure to latent space, and the compressed image is called latent. How it does that? It uses variational autoencoder. So autoencoder, like encoder part, it utilizes to compress image into latent, and then the encoder part stores the as I told you before, natural images are like not just random. They mean something. They have a special relationship. I give you the example of face. A nose will be below the eyes or above the lips. So that is like fixed. So that is the special relationship I am talking about. So encoder part, so how okay, so let me clear you one more question. Like how is it even possible, if we are working on compressed version of it, so how is it possible it will not lose any information? So yeah, so I see the images are mostly resolution. And so what the variational autoencoder does here is it only captures the relationship part. It does not mind the unnecessary details and remove that high resolution. So we don't need that or unnecessary details. But it will also only capture the spatial relationship, like the features of the nose, lips, and when it will capturing the face of picture of an face. So it will only keep the spatial relationships like a nose or lips or ears and all. So it will so that can be stored in much less space and in much less latent space. So that is how the latent space is even possible. So yeah, so it uses variational autoencoder. It is on autoencoder. It is very good. So yeah, so it is the encoded part is used to compress images into latent, and then it store the spatial relationship to because it will have to later the decoder part have to reconstruct original image from latent after diffusion is after diffusion process will be completed. We need to again resize the latent into the original image. So it previously stores the spatial relationship while encoding, and then we use that relationship part while decoding. So yeah, this is the image representation of it. Like the first, the image is of 3 into 512 into 512. Then we pass it into VAE encoder, and then we can see here it is the latent representation is only of 4 into 64 into 64. And then we use the decoder part here of it. Like after we will pass this latent representation to the like diffusion model, and after the all the steps will be completed, then we will pass it to the VA decoder. It is the last step, and the image only is only passed once to the VA decoder part, and then it will regenerate the previous the previous dimension image, which is 3 into 5 into 5 into 12 into 5. So this is what makes it like so faster to train, and it is like the month's training can come into days. This much amount of like fasting can be happen. So yeah, so this is how the latent diffusion, latent space works. So yeah, this is the main more mathematical architecture of the stable diffusion. So let's understand it.
You can just give an overview, that's all. Okay.
Yeah, okay, so let me, okay, well, I can guide a little. So yeah, so this X part is the input image if we provide any, to be honest. If we don't provide, then it will be a random noise generated from random noise generator. This E is the encoder part. And this is the, as we can see, pixel space. Pixel image like that, where the original image exists. This is the latent space. So here we will pass the like encoder will encode the image into a latent representation, which is like much more lower dimensional. So this Z will be the latent representation of it. Then it will become like ZT, the diffusion process. It is the forward diffusion process, like which I explained when the image to image encoder part. So it adds like a unnecessary image to cover the like the unnecessary detail, like a dog on the bench. So it will cover the dog part with random noise. So this is the forward diffusion process. So if we provide an image, so this will happen. If we only provide a random noise in starting, so the forward diffusion step will not happen. This is the ZT. Then here is the reverse diffusion part. This is the reverse diffusion part in the background. And this is the conditioning. Conditioning, like it is the text conditioning. So this conditioning part is providing like the text information to it, like how we want our final image to look. So so this is the like cross attention QKB module. This is the cross attention modules. Cross attention modules are used to emphasize more on the text, like what we use. And we use skip connection to that. Skip connection, like it was first introduced in residual networks. So like it was a very good idea. Like the idea was to like when the neural networks were of very deep and consist of many layers. So the future layers didn't have much information. Like they started forgetting the information which they learned previously. So then the skip connections were like introduced. So like there is a layer number 5. So we will include, for example, so we will include a skip connection from layer number 5 to layer number 8. So like in this way, the information in layer number 5 directly passed to layer number 8, and this is how we conserve the information in long network. So the cross attention module, this is like more to this is the main, like where cross attention and skip connection mainly where the text emphasis happens. This is the denoising step. Here it comes. So here the denoising process happens. Xt minus 1, t are the step number, how many steps we want to convert. And we can also see that this is the concat part. So like the text information, as you can see, it is passed directly to the denoising step, and it is also passed to the input, like cross attention mechanism. So here we pass it to the cross attention to like to more emphasize on it, and we also include these skip connections to like retain the information and in longer well, like stable diffusion also consists of so many layers. So to retain the information, we use the skip connections here. So this is generally the architecture of the stable diffusion, and this is how it works. And at last, when the T steps are completed, it outputs Z. Z is the latent, still the latent representation of the image. Then this is the D, the decoder part, and then X hash. This is the output image, and this is the like image which we wanted to generate. So this is the architecture, or the I will say the
at the time of inference, right? We don't have X. So that at the time of inference, this is at the time of training, we have the image also, right? So X is that image, correct?
Yeah, X is the input image.
So let's say at the time of inference, we don't have that image, right? At the time, will that be just a random noise, or this whole part of latent space will not exist?
It will be like, it will be the random noise.
Okay.
Because it is trained on the image, so image needs to be there. Like what it will output, because it's an image generator. So the image, random noise is also just it is a representation of an image, but the only difference is that like that image doesn't mean anything. Like here you can see in a
Yeah.
step one, so this is also an image, but the only difference is it doesn't mean anything. And after step 40, it does mean something. So that is the difference between random noise and
My question was that let's say should we feed, does it feed X into the network at the time of inference as a noise, or does it cut short of everything and feeds noise at ZT? ZT is there in the diagram, right?
yeah, yeah.
So I believe that it would be because extracting the latent space from a random noise would be just useless exercise. So instead, you could just generate ZT randomly, and that's it, right?
No, so like okay, so let me explain it more clearer. So you are asking in during the training process, if we don't provide an
No, not training, inference space.
yeah, during the training.
No, inference.
Oh,
Once you're using the model, because at the time of when you are using a model,
yeah,
you
yeah,
you don't have the image to feed, no?
yeah. Oh, yeah. That's how I answered in the starting. Like if it will be randomized, so the diffusion process will not happen.
Yeah.
So, but diffusion process
No,
doesn't happen.
my question is, you said we'll feed random noise, correct? In that case.
Mm-hmm.
So is it that we are doing ZT as random or X as random?
X is random. X is random.
Okay. So we let that X go through the entire latent space.
Yeah, but it will not. The only one part which will be remaining is like when we pass an image, we also add a noise, as I explained. But in if we will pass it the random noise in the starting, the image the noise addition part will not happen. We will not add further noise to it.
Okay.
So
Okay.
this will be the
Perfect.
difference.
Perfect. Perfect. Great answers. All right. There are some questions. I'll take up those questions now. Okay.
Just 1 minute. Just
All
one.
right. Okay. Okay.
2 minutes.
Okay.
Okay. So like they said, the denoising process, which happened, in the starting, you can see it is like a much more like a unclear image, but it generates a high resolution image of a cat. And then the decoder part, as I explained, this is the same decoder, which is like here, VA decoder. Yeah. So VA decoder, this is the part which we are talking here. So yeah. So it reconstructs the latent image to a high resolution image, and it runs only once at the end of the process to produce the final pixel image. So like latent image, which is compressed information is stored by the encoder, which is passed to the decoder to use it to reconstruct the image to a original size. So a stable diffusion training data, it was trained on line 5B, and the version 1 for 1.4 was trained on 3 subsets of line 5B. One is line 2B, and you can explore that at the stable diffusion website. Yeah, so it also has some limitations. So what are the limitations? So yeah, it has issues with degradation and inaccuracies in certain scenarios. Like initial releases of the model were trained on dataset that consist of 512 into. Yeah. So the images with the initial release of the model were trained on 512 into 512 images, but so it was not able to work much accurately on other resolution images, like to generate 768 into 768, as it were trained on it 512 into 500. So that was a most limitation, and it is also fit by the current models, but only a little bit, because the version 2.0 update can also work on the 768 into 768 resolution. Also the line database which the model were trained on, it is much more it has much less features for the limbs data. Like here we can see like 2 arms are there generated. We can see like here the limb is incomplete. Here also we can see like a minor detailing of option is there. So like this is also this is only because line database doesn't have much, doesn't capture much of the limbs information. So this is why it happened. Customization, like in order to customize the model, like you want to use for other tasks, so you will have to further you have trained it so much, and you will have to generate the new data to train it. So like it is not much customizable as it was thought like to be customized, but not that customizable. So yeah, so this is like here are the limitations. These are the limitations.
Wonderful. No, so yeah, I just want to take some questions now. I'll take one question at a time. Yeah. Let's go back to the architecture. Probably we can. One question from Dinesh is, which encoding stable diffusion model is using? So question here is that do we convert the text into representation using something like a GPT or something, or do we train it from scratch?
So yeah, so as I told, because we use the clip model. The clip model is of OpenAI, the same OpenAI, like the same model which made ChatGPT. So yeah, we use the clip model which we use in Stable Diffusion. It is already trained.
Okay, it's
So
only fine-tuned here, is it?
yeah, it is only fine tune. Like we don't need to fine tune because the text encode, we only utilize the text encoder part, and it is also like it is like trained so efficiently, like it is able to generate much more like a much more closer representation to its image, like to its visual representation.
Okay.
This is the answer.
Perfect. Thank you.
Yeah.
A question from Jyoti Sekhar is that in clip, initially from where we get the image, initialization or warm up the neural network with the text to embedding, right? Yeah. So yeah, I think that is also answered just now. Okay, great. Another question is, so here, while adding the noise, is that based on image perturbation? So it's kind of image perturbation, but we do not do all kinds of perturbation. All we do is that we have an image and we basically generate random noise. Specifically, there is a term called Gaussian noise. And when you are generating Gaussian noise is essentially the way it is that we give the median value and it generates the data nearer to the median based on the spread, standard deviation, right? And is that right, Shub?
Yeah, that is right.
Yeah.
We just have a question, right?
Yeah. So we basically generate, like, let's say a bunch of numbers randomly. These numbers are closer to the median. And we basically add these values to the image. And when we say scheduler is nothing but what we are doing is we are, saying that, okay, how much effect this random generated value will have. Like what fraction, like what dominance, instead of having a simple average of the values, right? You take the image and you take the random data, you compute the average of the two, okay, and generate a new image. Rather than having equal weightage to both, we basically tweak that weightage based on the scheduling step, like which like if it is a lowest step in the scheduling, like it's 100th image, so the impact of the noise will be way more higher than the image. So it will be a weighted average rather than a normal average. So yes, so I hope you got the idea on adding the noise now. Good. I hope I made sense, Subh. Yeah.
Yeah.
Okay. Yeah, at any point of time, if you have something to add, I'll let you know. Okay, you can just let me know. A question from Nikhil is, how well can we find sentence or para similarity if we introduce diffusion in it? Will it be better than Gensim, Spacey, or cosine similarity? Okay. So yes, question is, yeah, it's let me try to understand the question. Question is, can we utilize the similar diffusion model for language as well? As a matter of fact, that technique has been used in past for language models. Okay, but the one that predicting the next word technique or predicting the next character technique seems to be much more impactful than that. Okay, and yeah, From the fact that most of the things that have come out of, like, say, GPT revolution, they are definitely better than Spacey or Jensen. And yeah, cosine similarity is something that we anyway do. Okay, so a common question is that where do we compute, use the L2 distance, or where do we use the cosine similarity, and so on, right? I think here when we were saying cosine similarity, that was a loss function, and in the other one, like what model was it? Clip, right? Yeah,
Yeah.
yeah, we were doing in the clip model. So that cosine. Cosine similarity is not really something you can compare as a model. It's just a loss function. So there are like multiple kind of loss function you have. One is simple x1 minus x2 square kind of we call that L2 distance. Then there is L1 distance. There is a cosine similarity. Then there are many other contrastive. There's forgot the name. Those are the different kind of loss functions. So yeah, I hope I answered your question, Nikhil. Question from Dinesh is why noise adding in the image? So the reason why we are adding the noise is that we are teaching it to, create image. Okay. It's essentially, if you look at most of these are, techniques to train neural network models to create or do things. Okay. Like what we did was we took an image, added the noise. Now we have a dirty image, we have a good image. We are teaching a neural network that this is a dirty image and this is what we want. And like tweak these knobs in order to generate a good image from the bad image. Now, as it learns to tweak these knobs, and by tweaking these knobs, we are making this neural network learn to convert a bad image into a good image. What happens is it essentially learns the art of creating. Okay. It essentially learns the art of creating an image, so much so that it starts creating things even from the noise, like a random noise completely. Okay. I hope that answers your question. A question from Bhagya is, sir, instead of image, is there any possible uh, to generate chemical structure? Of course. Of course, there are quite a few things you should take a look. You can use the same philosophy in case of the chemical structures. And yes, as a matter of fact, I have done it for the crystal structure. Like instead of generating crystal structure, I was just analyzing it. But it's definitely possible to do those things. Instead of text, like you should take a look at the generative model and see if you can tweak the same model for the chemical structure. And yes, of course, the similar thing you can also, if you have good amount of data for training for the chemical structure, you can use the stable diffusion as is. A question from Bhupinder is, so their images are just attached to abstract data, then proceed to text to image. So these images are just attached to abstract data, then proceed to text image. Yeah. So images, the reason why we were doing this image one, we are teaching the UNet, right? No, the diffusion process. Okay. We were teaching it to come up with numbers that represent an image. Okay. It's like building an understanding of something, and that we do in almost everything in neural network. Because if you think about neural network, what neural network does is one layer generates bunch of numbers, those bunch of numbers are fed to the next layer, and so on. So every step is kind of creating new features for use case in using in the somewhere else. Correct. So essentially, this process is about learning to create image and learning to convert image into some representation, meaningful representation. Okay. All right. Next is machine gonna think and visualize it in their CPU just like animation? Yeah, that was the idea, the animation that Shubh was saying. Shubh, can you show that animation? Yeah. So this is essentially the same thing. It's basically more noise, less noise, less noise, and then yeah. So this is how it's going to do. Instead of, unlike humans where they paint the picture from left to right, it's essentially painting the whole picture one step at a time. All right. Left to right, top to bottom. That's how usually most of the painters do. But here, it's essentially impacting every pixel in every step. A question from Shivangi is, do we need to train random noise generator based on all the images? No, we don't train random noise generator. Random noise generator is nothing but generating bunch of random numbers. It's just saying NP random, or it's just using that Gaussian noise. How do you do that? I think you can pass that parameter to NP random. Okay. So moving on to the next question. Question from Dinesh is, when we want to generate image to image, do we need to provide some text with the input image? Of course. That's what we were saying, that the text will get converted into its semantic meaning. And then we are feeding, instead of a random image, we were feeding the image and it was manipulating that image. All right. A question from Gayatri is, from where do we fetch the images data to train? Yeah, he mentioned, like Shubh mentioned, that FAI, what was it? LION data, right?
So you can see it from here, like
Yeah,
land 5.
yeah. Lion data. You can take a look at that. So that's what is usually used. Okay, wonderful. Thank you. Question from Dinesh is, can you suggest few good study materials to know more about stable diffusion? I think you can start with the Wikipedia page, or yeah, you can also take a look at the paper of the stable diffusion. That could also be helpful. Okay. A question from Tasin is that why not directly subtract the noise predicted after each instance step from the latent? Okay. So question is, what we were doing is, in the diffusion, in case of diffusion, we were predicting the noise and then subtracting the noise, right? There could have been other approach that we basically predict the outcome image itself, correct? So that's a hard thing to argue, but hard thing to debate. But the core idea is that it's easier to compare the noise as compared to comparing the image itself. Okay, so therefore it is better to just let that noise be there, because we know the noise exactly and it is easier to compare that noise. Okay, wonderful. A question from Shivangi is that for training the diffusion model, is the image and data pair in the same context? Correct. So you take a look at that data set. What they have done is they crawled the internet, extracted the captions and other things from the internet, and then labeled it. Okay. Now, okay. A question from Vamsi is, can you suggest thesis ideas where we can use stable diffusion? I think there are so many use cases you can come up with. To think over it, look at it, tinker around it. You will definitely get lots of ideas. Okay. A question from Vivek is, so basically the output is not a new creation. It is only producing one composite combination from the millions of existing. Not really, not really. That's not how it does. It's not selecting it. Okay. It's not memorizing those images. That's the important part to know. It's not memorizing those images, and it's, you can also add more things and it will create new things. If you saw the imagen.google.com, or you take a look at lots of data set, there are new things it has created. Okay, the only thing is it would not know a new word. Let's say dinosaur data is not there and you ask it to create dinosaur, right? Probably the language model would try to represent dinosaur as a dragon or something, and then maybe it can create something. But if it is not trained on dinosaur and the language doesn't know what's a dinosaur, it won't be able to create it. Okay. So it's not essentially only assembling of the images. It's also a composition of the image. Okay. A question from Arpit is, so can't any model create an image from nothing, no noise image with only text input? You have to train it. You have to train it, and then it can definitely create image. The agenda with respect to feeding that random noise was to be able to edit the image later on. Okay, creating a progressive editing. That's the main idea behind feeding the random noise. Is there any other idea, Shub?
No, I guess there can be several ideas, but currently I don't know of any.
So I think the reason they are feeding the random noise is so that it can be progressively edited.
Yeah. That's right.
Okay. Everyone, thank you so much, and thank you, Sub, for wonderful presentation. Everybody, there is a new course coming up, right? It's a couple of in a week. So this course is essentially executive PG certificate program in data science and AI. All of the ideas that we have discussed in today's session, those are taught in much more detail along with machine learning and other parts as part of this course. So this course is a good combination of both extremes, theoretical knowledge as well as applied knowledge, because it's a combination of IIT professors as well as the industry experts. So I can assure you that you will have one of the best learning experiences in India as well as outside as part of this course. This is fairly deep dive and broad enough, and yeah, this will help you improve to a very large extent. All right. So yeah, thank you so much and have a good day. Thank you, everyone. Have a good day. Question from somebody is that will the content of this course be available on premium subscription? So premium subscription includes our courses. We do have deep learning courses, but the IIT course is not provided as part of the premium subscription because that's not ours. Okay. All right. So wonderful. Thank you, everybody. Reach out to us at any point of time. And this course with IIT is basically part live. I mean, there will be classes by both industry experts and professors. All right. Thank you so much. I hope you guys liked the session, though it was fairly technical, and I'm happy that so many people came to attend it. I was not actually expecting that many people. In case of ChatGPT, I was expecting good numbers, so we had around concurrent 1,500 or 1,700 people in the live talk, and but still, I'm like super impressed with interest level of all of you, and because these things are really important. These things are what makes or breaks a career today. And in the recent time, the machine learning, AI, the research has moved really fast. Academia is trying to catch up with what's going on. Industry is still finding very hard. And usually people have the machine learning on their to learn list, but they just because there's no external commitment, they keep on postponing it for years and they never end up learning. Okay, so I think it is now, you should start right now, whether you are, no matter which domain you are in, you should take up data science and AI as your, commitment this year. Okay, because I think the whole world has moved that side. And right, it's a new discovery of things which is essentially going to impact the way we think, we work. Professions are changing, new professions are coming, and so on. So this is the high time to be, data science and AI literate. Otherwise, it becomes very difficult. Okay, so my request will be, whether with us or somebody else, enroll into a data science and machine learning course, specifically the course that covers deep dive. Okay, not only the regression and decision trees. Okay, into neural network. Neural networks have gone way beyond. While machine learning, probably the kind of research in machine learning has happened is mostly like classic machine learning, statistical model RPT. Not too much has happened that side. All right. Thank you so much. And really happy to have all of you in this session. Okay, so I'll just end the stream.